This is Euclid Book 10, proposition number 47, and please don't switch off this video after I finish my presentation. I'm also going to present some new Book 10 definitions. Okay. Now here is the diagram. Looks pretty complicated, doesn't it? Okay. And here's the proof. The side of the sum of two medial areas is divided at one point only. Let AB be divided at C so that AC, CB are incommensurable in square, and make the sum of the squares on AC, CB medial and the rectangle AC, CB medial and also incommensurable with the sum of the squares on them. Sounds really complicated, right? Okay. Let's take this one step at a time. Now, the lines AC, CB are incommensurable in square. Okay. Here's line AC and here's line CB, and these two lines are incommensurable in square. Okay. And they make the sum of the squares on AC, CB medial. Okay, what does that mean? We're going to make two squares. The first one is AC. All four sides of that square are going to be the length of AC. The other one is CB, and all four sides of that square is going to be the length of CB. Okay. And the rectangle ACCB medial. Okay, so now we're going to draw a rectangle. Two sides of that rectangle are going to be the length of AC. Two sides of that rectangle are going to be the length of CB. The area inside that rectangle is going to be medial. Okay. Now, the area inside of that rectangle is going to be incommensurable with the sum of the squares on them. Okay. So that means, you remember those squares we just drew? The one that was AC, the other one that was CB? If you add those two areas together, they are going to be, that whole area is going to be incommensurable with the area of that rectangle. That's what it's saying. Alright. I say that AB is not divided at another point so as to fulfill the given conditions. For if possible, let it be divided at D, so that again AC is of course not the same as BD. But AC is supposed greater. Let a rational straight line EF be set out. Okay, so now we're going to say that AC, the line AC, is greater than BD. Okay, so now we're going to say that AC, this length right here, is going to be greater than BD. Then we're going to set out this line called EF right here. Okay. And let there be applied to EF the rectangle EG equal to the squares on AC and CB. Okay, so we have a rectangle, it's called EG. And actually it's EHGF. Okay, EHGF is a rectangle. And the area inside of that particular rectangle is going to be the same area as, okay, so hold on, we've got one area. Now we're going to compare it to another one. Okay. The other area we're going to compare it to, you remember those do you remember those squares? The AC square and the CB square, we told you to add those two areas up together. Okay, the area that I'm talking about, okay, you take the area of AC, you take the area of CB, you add those together, that area is going to be the same amount as what you'll find in EFGH. Okay, so that area right there, and we're including this all the way from here to here. All that area is going to be the same as the area of the squares AC and CB. Alright. Going right along here. And the rectangle HK is equal to twice the rectangle ACCB. Okay, now we got HK. What is HK? Well, HK is HGKN. I'll show that to you. HGKN, that area right there. Now, what is this area equal to? Well, do you remember that rectangle we drew that had two sides the length of AC and two sides the length of CB? Okay. If you take that rectangular area and you multiply it by 2, you get this area right here. Okay. Therefore, the whole EK is equal to the square on AB, which is by Euclid Book 2, proposition number 4. Okay. So, what is the area of EK? Well, that's the area of ENKF. This whole thing right here. That whole area there is equal to something. What is that area equal to? Well, if you take the line AB and you make a square out of it, okay, so all four sides of that square are going to be the length of AB. That area inside of that square is going to be equal to all of this. Okay? All right. Again, let EL equal to the squares on ADDB be applied to EF. Okay, what is EL? Well, that's EMLF. That's this area right here. EMLF. And this area is going to be equal to something. What is this area equal to? Okay. Do you remember when we drew the square of AD? Okay, we took the length of AD and we made a square out of it. And do you remember we took the length of DB and we made a square out of it as well? If you add those two areas together, that area inside those two squares is going to be the same area as this. That's what he's saying. Okay. Therefore, the remainder, twice the rectangle ADDB, is equal to the remainder MK. Okay, so what's MK? Well, MK is MNKL. This whole area right here, this part and this part, all together. And that area is equal to, that whole area is equal to, do you remember that rectangle I told you to make? And two sides are going to be AD and the other two sides are going to be DB. Okay. The area inside of that rectangle, if you multiply that particular area by 2, then you will get the area of all of this right here. Alright. And since by hypothesis the sum of the squares on AC and CB is medial, therefore EG is also medial. Now we're going to say that the area of this plus this here, all of this together, is going to be medial. And it is applied to the rational straight line EF. Okay? Therefore, HE is rational and incommensurable in length with EF. Okay, so what is HE? Well, HE is this line right here. It's rational, but it's incommensurable in length with this one. Okay, so far so good. And all of this is true because of Euclid Book 10, proposition number 22. For the same reason, HN is also rational and incommensurable in length with EF. Okay, so now we have to show you HN and EF. This line is rational, but it's incommensurable in length with EF. And since the sum of the squares on ACCB is incommensurable with twice the rectangle ACCB, therefore EG is also incommensurable with GN. Okay? So this area and this area combined is incommensurable with this area right here. So that EH is also incommensurable with HN. Okay, what is EH and HN? Alright. Line EH is incommensurable with line HN. EH, HN. That's what they're talking about. And this is by Euclid Book 6, proposition number 1, and Euclid Book 10, proposition number 11. Line EH and line HN are rational. Therefore, EH, HN are rational straight lines commensurable in square only. Okay. Therefore, EN is a binomial straight line divided at H. En is a binomial line divided at H. And that's by Euclid Book 10, proposition number 36. Similarly, we can prove that it is also divided at M. And EH is not the same with MN. Okay? EH is not the same length as MN. Therefore, a binomial has been divided at different points, which is absurd. This is by Euclid Book 10, proposition number 42. Therefore, a side of the sum of two medial areas is not divided at different points. Therefore, it is divided at one point only. And thus ends the proof. Now then, I told you I had some definitions to read to you. Given a rational straight line and a binomial divided into its terms such that the square on the greater term is greater than the square on the lesser by the square on a straight line commensurable in length with the greater, then if the greater term be commensurable in length with the rational straight line set out, let the whole be called a first binomial straight line. Okay, now when I make my next presentation, I'm going to draw all this out. So I'm just reading it to you this time, and in the next presentation I'm going to draw this out. Alright? But if the lesser term be commensurable in length with the rational straight line being set out, let the whole be called a second binomial. And if neither of the terms be commensurable in length with the rational straight line set out, let the whole be called a third binomial. Again, if the square on the greater term be greater than the square on the lesser by the square on a straight line incommensurable in length with the greater, then if the greater term be commensurable in length with the rational straight line being set out, let the whole be called a fourth binomial. If the lesser, a fifth binomial. And if neither, a sixth binomial. And that's your definitions. I will try to draw all of this out for you in my next presentation. I will tell you more in my next presentation, so stay tuned.